I will be presenting about this fluid turbulence simulation in 2-dimensional or 3-dimensional. Basically, it will be 3-dimensional in a plasma boundary. This is the very common part where mostly code will be involved. And using the same code, I will be talking about ELM blob merging phenomena. This is about turbulence in boundary region of a plasma. It can be various situations like linear device, tokamak, ionospheric plasma. Basically, the plasma where plasma is bounded by axial magnetic field. As it is bounded, it has lots of free energy, and these free energy can give rise to instabilities. These instabilities are typically Rayleigh-Taylor, drift, interchange, also sometimes Kelvin-Helmholtz, is not written here. These are highly nonlinear in nature. Very few of them can be described analytically, so it needs numerical simulation. We will describe boundary plasma turbulence in edge region of tokamak, but I told these are the situation where the same code can be applied. Now come to the edge region of a tokamak plasma. All of you know that edge region where magnetic field lines close themselves, but it is in the boundary region, just inside the last closed flux surface, where tokamak plasma is interchange in nature, turbulence is interchange in nature by also another instability mechanism, that is peeling ballooning mode. This instability creates plasma blobs. In the scrape-up layer, only the interchange instability, but in the case of edge region, it has a combination of peeling, ballooning, and interchange. Peeling, ballooning have a interesting features that generates blob is that these blobs are unidirectional current. Whereas in scrape-up layer, these blobs are basically dipolar in nature. So these blobs, as the definition of blobs is this, they are characterized by long elongation along the magnetic field. In the perpendicular direction, they are localized, just like a circular or circular shape. But it is not Gaussian, but theoretical people can express it is just like a Gaussian in 2-dimensional space in the perpendicular direction of magnetic field. What I will be talking about, the plasma blobs. These are the blobs which are originated from type 2 and type 3 ELM ejection mechanism, not type 1, because type 1 is very gigantic, where only single blobs or few blobs ejects, but type 2 and type 3, a large number of blobs comes. Large number is important for this presentation purpose or this type of work purpose, because large number, when it is, then they will come close each other, and then there will be interaction to each other. Whereas type 1, this will not be there. That is why type 1 is excluded from this, and type 2 and type 3 is included in this presentation. Okay. Now I am coming to the MHD sorts of equation. The first equation is very clear, density continuity. And second equation is current conservation equation. Sometimes it is called quasi-neutrality, because electrons and ion density both are same, charge densities are same. And third one is generalized Ohm's law. Again, it is a very simplified form, where it is a fluid picture, where velocities can be expressed by E cross B. Okay. This is E cross B, and then V star is diamagnetic and polarization drift for the ion, for electron it is not. And then standard definition of current density and standard definition of electric field in the case of electromagnetic in nature. The same equation, if I do little bit manipulation, then equation will come to this form. This current density J parallel, perpendicular part that is decomposed by the right hand side G, and again the second equation is divergence of J, that is quasi-neutrality equation. Again perpendicular part have a polarization drift, and right hand side that is maybe the diamagnetic. And generalized Ohm's law, again decomposed by other things. And as this set of equation we need to normalize. Normalization is very standard, like a standard density. Time is with the ion gyro frequency. Space coordinate by gyro radius, vector potential by V0 rho s, and potential is like this. These are the normalization used here in this equation. Then three equation comes like this. Now the code what we used, that is Baud++. At the same time, Baud++ is very difficult to use because sometimes when input parameter is difficult, very difficult to identify. So we develop another code that is related to the Python, but both I will be talking about. Before that, the coordinate system used, this is simply X, Y, and Z, not like toroidal coordinate, because it is very simple to do numerical work. X represents radial, Y represents poloidal, and Z is toroidal, means the direction of magnetic field. But in case of other, like whatever I told, linear device or ionospheric plasma, the same code can be used. Again, Cartesian coordinate system. The boundary condition used is Neumann along X and Z. Sometimes people use Z direction is again periodic, and Y direction is solely periodic. Now, as I told, it is a Baud++ code. Again, this code, only one code is not enough for this work unless it is properly benchmarked. So it is again benchmarked with, means code is benchmarked with Python. Again, Python is benchmarked with this code interchange, means result is checked. Python I used because it has its lots of libraries like NumPy, SciPy, and Matplotlib. These are inbuilt, no need to do anything. And it has many other like Poisson solver, Poisson brackets, time integration. These are the code written in Python. It is there in the library. And another advantage is that it saves data in inbuilt parallel libraries without doing any special programming for that. And each function and subroutine, as I told, parallel is done by number. It is very high, means higher end use. Number is another maybe module for that. So this makes it is a framework type. Framework in the sense that we no need to write corresponding function. It can be directly called. Similar facility is also available in Baud++. That is why Baud++ is highly framework type. So both of this code, the like finite difference in X and Z, using numpy.pad, that is the boundary condition we can use, like Neumann, Dirichlet, and periodic. FFTW3, both code have used FFTW3, no need to write down code, only the calling function. And then Poisson bracket using appoint first order and second order. Baud++ have again fourth order. Arakawa scheme again second and fourth. And UNO, essentially non-oscillatory scheme. This is related to the finite difference, but code can be called directly. Again, Poisson solver is solve banded. It is in Python, not in Bout++. Time integration or OD solution can be done by RK45. DP means this is another name. Then BS23 Adam Westport, again SSP3. I think this is very stable RK3 methods, it is there. And data saving is like NumPy append module, it is done in parallel. Corresponding all facilities available in Bout++. We identify both the code can be done very effectively and all are parallel. Now I'm coming to the input parameter for the tokamak plasma. The input parameter we took, that is very high beta plasmas like ITER. Density is high, 10 to the power 14 per centimeter cube. Around means 10 to the power 20 per meter cube. Electron temperature is 200 electron volt. It is in the edge region, not in the core region. So that is why temperature 200 electron volt. V0 is 5.3 Tesla. R means measure radius 6 meter. Corresponding derived parameters, if I calculate ion gyro frequency, this is around 2.64 into 10 to the power 8 per second. Rho S means ion gyro radius, 3.7 into 10 to the power minus 2 meter. Sound speed around 9.98 into 10 to the power 6 centimeter per second. These are the three derived parameters has been used to normalize the case, different variables. Okay, now I'm coming to the plasma blob simulation. So before that, let us describe plasma blob. As I told, plasma blob, these blobs are basically unidirectional current, not like dipolar. When blob propagate much inside, means much outside to the tokamak, higher radius, then these are polarized by charge polarization, by the curvature drift, and then it will not be a monopolar or unipolar. It will be dipolar. But here, presentation is given in case of monopolar blob. That is the second equation here. And the first equation, first means presentation of the blob, it is NB is the background density, 1 is taken for a safety, so that code will not diverge, and this is basically combination of two. Y direction there are two location of blob, and X direction X0 is the position of the blob. That means first equation gives presentation of a blob, two blob that are polaridally separated, but toroidally means radial position, it is at a position of X0. So corresponding current density I told. So now doing this presentation of this description of this blob, this code has been benchmarked theoretically. This is energy. As I told, there is a periodic function and radially Neumann, then this type of conservation equation holds good. So we check this conservation. Now in the next slide, this conservation is given here. The horizontal line corresponding different grid resolutions we have taken, this is 3D. Then it is a perfectly straight line. That means conservation is there with time. Time is around 1500 gyro time. So this is accuracy is 10 to the power minus 8. So this is established that code is doing correctly. As I told, these two blobs are taken polaridally. That is, top one is Y1, bottom one is Y2, and radially X0. This code, now I will be talking about what means blob to blob interactions. The blob basically unipolar current, and these are the toroidally elongated. That means this is a two current carrying wire. Two current carrying wire, we know in the whenever current in the same direction, they attract each other. This similar thing happens here. They attract each other, and at the same time they rotate. That is the second figure. What is the rotation of this figure B? And after some time, this is getting bigger size. That is because of this diffusion. And they rotate and finally merge each other. So this is the merging phenomena. This type of blob is type 2 or type 3. In the presence means whenever they are in large number, they get a scope to interact by this electromagnetic way. And initial current density we took 0.5. This is 0.5 means around 1 mega ampere per meter square. It is normalized. So it is a huge amount of current in each blob, and they interact and they almost come close each other, and this is a merging phenomena. The corresponding vector potential, we took the another approximation that ion temperature is 0, means cold ion. And what will happen for the hot ion, I will be talking the next part. The cold ion, that vector potential is different. You see the color bar, vector potential there increases after interaction with the plasma. And whenever they come close to each other, that means magnetic field is different, means higher. Higher magnetic field means they attract very strongly. That is why whenever they are coming closer, they attract strongly and finally they merge. So this is the merging physics where vector potential A parallel is described by this function. Now I am coming to the growth rate. See, each blob, magnetic field increases. As I told, means A parallel is increases, and A parallel growth rate is 10 to the power minus 2. It is basically very similar to the age turbulence case. This is the normalized 10 to the power minus 2. So, after some time, this increase, you see, growth rate is almost steadily increases, and then there is, because of this, lots of non-linear effects. Now I am coming to the case of finite ion temperature case. This earlier these works was published, and this work is not yet published. We are doing in this work. Interesting point is that whenever ion temperature is taken into account, earlier ion temperature was 0. When ion temperature is taken into account, that means these blobs have both electron temperature, ion temperature, and also the density, which are the maximum at the center of each blob. And then they come into closer. The top one already presented earlier. Here it is presented both of this case to compare each other. Earlier in the cold ion case, you see both merge together. But whenever hot ions, we find that they maintain their coherency for a longer time. They move in the polar direction, and after some time, we find that they do not merge each other. They maintain longer time. So that is a very interesting phenomena. That means merging and non-merging is a different case. It is a signature of ion temperature. When ion temperature dominates, this happens. Coherency maintained for a longer time. So this tau I put somewhere. Okay, this tau is not there. Okay, tau means Ti by Te. It is coherency maintained for a longer time. Now, important fact is, whenever Ti taken into account, Ti, this is the means red plot. This is Ti case, and this is tau means Ti by Te, and this is finite ion temperature, electron to ion temperature ratio. This case is 0. We find that the distance they are not coming closer, because after long time their distance of separation still remains. So the distance of separation is measurement was another issue, because this is a blob. It is not like a single presentation of a particle. So the distance between them is basically distance of center of mass. We wrote that thing in the paper. This distance of separation between distance of each center of mass, distance between each center of mass. Okay, now this is my last slide. This is a physics of ion temperature. What makes special that if ion temperature is taken into account, both blobs does not merge each other or stay for a longer time? Why coherency maintained for a longer time? It seems that theoretically it is very logical. Whenever ion diamagnetic drift is there, that means the blob axially elongated, and azimuthally there is a current, that is because of ion diamagnetic drift, and this current make axial magnetic field. As current density is very high, axial magnetic field also will be very high. It will disturb the parallel magnetic field. So magnetic field will be less, and that means they will attract with a lesser force compared to the case of Ti is equal to 0. So they will not come into closure. Some simulation we find this is the behavior, and some simulation we find no, this is not the case. Magnetic field coming little less, but not so much substantial. That means there are some hidden physics inside of it that we are looking the next work. So this work is going on. This is my talk, and finally I am coming. Thanks.
Thank you. You finished 2 minutes before 25. First person to do that. Question? Yeah, one there first, and one here, one here, one here. Okay, I think I'll start from here. We have plenty of time, don't worry.
Okay, no, Nirmal, nice talk. The fluid simulation and when you compare with PIC simulation, so there you actually you do the details, the actual deal with the particles.
Actually, can you speak little?
Okay.
Keep it away.
Is it okay now?
Further away.
Further, no, it will go inside my mouth.
Further away. Away.
Away? Okay. Right?
Yeah.
So basically when we write the fluid equations for a given system, so we make some kind of approximations or assumptions that like for a given system, we can keep this parameter or that parameter, which will actually bring out the physics of that particular dynamics for set of equations that you have given or presented.
Just a minute, I didn't listen you properly.
Can you tell me?
I'm asking that what are the assumptions behind the set of equations that you have written. So to give the
Can you
the physics,
explain your equations quickly once more?
See, the first equation is continuity, no source. That is why 0 is taken into account. And second equation is assumption is quasi-neutral. So that is why time derivative is not taken into account. Now you are talking about tokamak case, that is different geometry, and why this is applicable here. Yes. Okay, that is why this linear device can be done. You can say that linear is a cylindrical geometry, but as far as colloidal length is taken higher than this correlation length, then it will be applicable, even it is a rectangular coordinate.
Maybe we can discuss that later. Madhurya?
Okay, thank you very much for the talk. I am
Yeah.
a little bit familiar with that because of this Obix work. Anyway, do you have this some term missing in the third equation, or it is like that only?
Which one?
Ohm's law. I mean, it shouldn't be E plus V cross V, or third equation.
Yeah. This is
No, the third equation.
third equation. This is generalized Ohm's law.
There is a
He's going to the
J cross B force is not
okay,
taken into account.
Okay, okay,
Because B and J are
right. Okay, now you are doing an MSD fluid equations, right? So where you might need a Poisson solver, I mean, you are not solving the Poisson equation.
This is in turbulence case. The Poisson equation normally is not solved. Because Poisson means del par square phi is equal to Ni, means Ni minus Ne, like. In turbulence case, this Poisson equation never comes. It comes through this J, whatever J with J is equal to del par square A parallel, that type of. Or even vorticity, the next equation, this one, potential whenever it calculated, it will be there.
One more question. Please ask.
Thank you for the nice talk. I have two questions. First, regarding equation 3, what is the motivation of keeping the electron pressure? Second, you showed that for when ions are not having any temperature, then the dynamics, and when ions are having temperature, then the dynamics are different. Can you not explain it in terms of plasma beta or the thermal pressure? Because if ion have some temperature, then they will contribute in the pressure, right? And the pressure will hinder the blob coming close to each other. Thank you.
Means you are talking about ion response?
Without any temperature, they are cold ion, right? And you are seeing that they are merging with each other.
Yeah.
And when you increase the temperature, then they are merging. They are not merging, or they're taking longer time to merge. So
So mostly you are talking about whenever there will be temperature, they will not come closer because of this motion.
yeah, there will be thermal.
Yes, it is there in the pressure term.
But that pressure, I mean, in your electric field equation, the pressure I do not understand. I mean, it's very easy.
Go to equation 3.
It will be here. The pressure term, if we, that gradient of pressure.
What is the motivation of keeping this gradient of P for electron? I mean, this is electron pressure, right? So what is the motivation of keeping this one? Because in collisionless system we have it.
Now
by
this
default.
is a fluid picture.
Yeah, but in collisionless system it will appear because the pressure is tensor.
No,
but
this is collisional.
yeah, but so I'm saying if you compare collisionless and collisional, in collisionless case the pressure will come because it's tensor. Now here it's scalar pressure. So what is the motivation? Are you modeling any pressure here, or what is the closure for this pressure? That's my first question. Yeah.
Okay, this is fluid picture. This gradient of pressure comes, and it is the blob which I am describing. It has this temperature, again described by this means collective motion.
Thank you for the wonderful talk.